Okay, on this first one, there's no real set way to do this. First, I make sure I have 7 vertices, so I just put all 7 there, and then I just connected something around the outside and kept track of the degrees. So at that point, I had degree 2 for every vertex, but I knew I needed 4 odd vertices. So I drew a line here, that gave me 2 of them. Drew a line here, that gave me 2 more, and then I had 4 odds. So again, it's more just playing around with the graph until you get what's required. Connected graph that is not Eulerian. So I again made sure that I had a connected graph. Of course, you have to know what Eulerian is here to answer this. So Eulerian, remember, is a graph that you could start at one point, trace over every edge exactly once, and return to that same original vertex. Or you can think of it in terms of how you analyze the graph. So it's a graph where every vertex is even. So as long as we make sure that there's at least one odd vertex, then it's not going to be Eulerian. So the other thing we need to make sure is it's connected. In other words, that you can get from any vertex to any other vertex by following the paths. If we had another vertex over here or a few vertices connected, that would not be a connected graph because this part would not be connected at all to this part. So we do have to make sure it's all connected and that every vertex is not even. Make sure there's at least one odd. Here, what we're looking at, you could do this in terms of a graph first if you want. For me, I just made something that was seven regions, and then I knew that these 3 are all bordering each other. It's kind of like the triangle in when we draw the vertices and edges. So I knew these 3 had to be separate colors, so I labeled them separately. Then I went here, well, this has to be a different color than both of these, so let's make it the original. I'm trying to keep the minimum possible here, which is why I didn't give it a new color. Then I go down here. Well, if this is red and this is green, this has to be yellow. Similar, if this is red, yellow, this has to be green. If this is green and yellow, this has to be red, if I'm trying to keep as few as colors as possible. So I am indeed able to do it with 3. I know it's not possible with less because these 3 right here have to be different colors. So I'm not going to get any better than 3. Here, we're essentially asking if there's an Euler path because we're not required to start and end at the same vertex. So what we're looking at analytically is, are there exactly 2 odd vertices or exactly 0 odd vertices? If there's exactly 2, there's an Euler path, meaning we can start at one of the odd vertices, hit every edge, end at the other odd vertex. Or if they're all even, like they are in this case, that means that it is Eulerian already. It means that we can start and end at the same vertex, and we could really choose any vertex for our starting point. And we do want to note that it's connected. We could not do this tracing, even if they were all even, if the graph were not connected. If there was one part of the graph over here and one part over here, and they weren't connected to each other, then it would not be possible. So as we mentioned, this is Eulerian. If it weren't, all I would have to do is start connecting the odd vertices until I made all of them even. And that would make it Eulerian. Nearest neighbor. So starting at the start, I'm looking for the lowest cost edge. So I have a 3, a 2, a 3, and a 5. I want to follow the 2. Here I'm looking at the 1 versus the 3 versus the 5. So I take the 1. Here I have a 3 here and a 3 here. How do I know which one to take? Well, I can't complete the circuit by returning to start. If I return to start, then I've just made a triangle here and I didn't include all the vertices in my path. So I need to go down here, and then this is the last one I have to hit, and back to the start. And by the way, by best edge, I would have started with this one and then this 2, and then picking my 3 would have been a little more challenging. I couldn't have picked this 3, but I could have picked this 3 or this one right here. Not this one, because that would have had 3 edges in the same vertex. But same idea, you're just going from least edge up until you have the 5 edges that you need in your graph. Okay, seating arrangement. I would encourage you to do these kind through a graph theory just so you can visualize it. So I'm putting the A, B, C, D, E, and F here. I'm putting an edge if they have common interests, and then I'm asking myself, can I find a Hamilton path through the vertices, starting and ending at any one, but maybe A, B, E, C, F, D, and back to A is one example. Then I can just line them up around the table in order of that Hamilton path. Spread of a disease. So just to clarify, this directed edge here means that E could pass the disease to F, but F could not pass it to E. So if I'm going from E to C, there's lots of ways that I could follow here. Perhaps the most complicated is G, F, B, D, A, C. Oops, nope, that wasn't right. E, G, no, what was the E, G, D, A, B, C. I think that was probably the most complicated of these 7 ways. And so the question we're often interested in applications is it possible that one of these could be the source of all of this? For example, it couldn't be A, because A could have infected B, and that could have affected D and C, but even if this entire group was infected, none of them could infect F, G, and certainly not E. So none of these 4 could have infected the entire group. As it turns out, E can infect F and G, F can infect B, G can infect D, D then affects A, B infects C, and you have the entire group infected just because E started off as infected. So it could have been a potential source of this disease. And then if you want to change as few as possible so that C could have infected everyone, well, right now C can already affect C, A, B, D, right? C infects A infects B, B infects D. So all 4 of these could already be infected, but somehow we need to get over to this group here. So you need to flip one of these 2 arrows. Doesn't really matter which one you flip, because then you have to flip the one over here to infect E. Once you infect E, you can infect everyone. We basically just need to get to E here. So potentially by flipping this one and by flipping this one, we could get out to E, and then from E we could infect G. So we need to change 2. So these I guess I didn't do them in the practice. The Roman numerals, we have the 30, and then in order to get a 9, we can't just put a 5 and 4 ones. We're never allowed to put 4 ones, but we could put a 1 before the X here. I'll try to do an example of these in the review on Wednesday, since I forgot there. 10, so 3, 1, 5, 7 as a base 10 numeral. So we write it in the exploding dots. We know what each place here is worth. This one's worth 1. Every dot here is worth 7. Every dot in this box is worth 49. 7 to the 3rd power, 7 to the 4th power, so on. So we have 3 of these 49s, 1 of the 7s, and 5 of these 1s. Add them all up to get 159. Down here, we're just adding 2 numbers in base 6. So we can add them directly, first of all, like this, just add straight down. But we know that in a 6-to-1 machine, anytime we get 6 dots, we're going to have an explosion over to the left. So for example, if we explode this 6 over to the left, this will now be a 3. This won't have any left. Same thing here. This will become 0, but it will give an extra 1 here. And then we'll end up with 9, which we know is ready for another explosion. So 6 of those will explode over here. That's why we get the 2. And the other 3 just stay around. So we have 2, 3, 0, 3, 0. GCD and LCM, again, several different ways to do it. I like breaking it up into the prime factors using a factor tree. So doing that, I get 18 is 2 times 3 times 3. 52 is 2 times 2 times 13. So there's 2 of those 2's times 13. GCD, I'm looking for, I have to make sure that whatever I find is represented in both numbers. So the highest power of 2 I can get is 1, because this one only has a power of 1. This one does have two 2's, but this one only has 1. And then this doesn't have any 3's, so I can't put 3's. This one doesn't have any 13's, so I can't put any 13's. So really 2 is the highest I can get here. LCM, I'm getting as many of each number. This is the greedy one. So here I get two 2's. I get both of my 3's from here, and I get my 13 from here. Multiply out to get 468. Totally fine to do that on the calculator, by the way. We check, so I know that GCD times LCM, whatever that number is, should be the same as multiplying the original two numbers together, which they are. Is 127 prime? So when I'm looking for a specific number, I'm checking up to the square root of that number. Here in this case, I know it's 11 point something. It's not quite at 12. 12 squared is 144. And if you need to use the calculator to figure out what the square root of 127 is, that's fine. But these I do want you to check by hand or by long division or by shortcut method, something like that. We need to check all of these primes. Well, 2 doesn't go into 127 because it's an odd number. It's not an even number. Does 3 go in? Well, if I add the 3 digits, 1 plus 2 plus 7, I get 10. 3 does not go into 10, so 3 doesn't go into 127. 5 doesn't go in because it doesn't end in a 5 or a 0. 7, I really kind of have to check here. So I knew that 7 goes into 140. That's 20 times 7. And then I started subtracting out multiples of 7. So 133, 126, and I noticed that I didn't hit 127. You could also start at 7. You could do long division with the 7. Anyway, you're going to find out that 7 doesn't go in. Same with 11. You could list them out. So 10 11s, 11 11, 12 11s. Notice we don't hit 127. Or you could set it up in a long division and find out that there's a remainder. But 11 doesn't go in. Since none of these primes go in, we know that no other primes will go in, and certainly no other numbers, so it is a prime number. In this case, two negatives. Here we have negative 1 times negative 1, so that would be a positive. 3 minus 6 gives us a negative. Adding two negatives remains negative. And when we get our answer here, we just do need to make sure we reduce it to simplest form. Here we do our parentheses first, so we get a common denominator and add these. Then we multiply it. Actually, I simplify it if possible. Before you multiply, it makes it a little easier. But then you eventually just multiply these across and just make sure that it is simplified. And in this case, it is.